Okay, so this is AP Chemistry section 2-1. We're in the middle of example 2 on the backside. And so we were looking for the rate law of the reaction. So what we have so far, we have the rate equals K as a constant times the concentration of permanganate. And we just found that permanganate is in the second order. Then we have ClO3 minus to the Y and the hydrogen concentration to the Z. And we are trying to write the rate law here. So we're trying to write this with X, Y, and Z filled in. So what we did in the previous one, we compared rate 2 with rate 1, and most things were able to cancel out. And so we were able to get X by itself and compare the rates here, and we found that the order was 2. So duplicate this. So we're going to follow the same basic procedure to find our next one, the concentration of ClO3 minus. So we've got a data table here on the notes, and so to look for this one, we need to see where does other things change and where do they not change. So if we compare, let's look at trials 1 and trials 3. So what we have here is, excuse me, the permanganate concentration is changing, but we also know that it's second order, and so we'll be able to work with that. And the hydrogen concentration is staying the same, and so ClO3 minus is changing. So let's go ahead and write these down. Let's compare what's going on so we can see the numbers. We're talking about comparing rate 3 to rate 1. So we're going to use the same rate law format. So for the rate of reaction number 3, we have 6.4 times 10 to the minus second, and that is molar per second, equals K, which is the rate constant. We have not found it yet. The concentration of the permanganate is 0.20 molar to the second power. Our chlorate is 0.3 molars, and that's to the Y, and our H plus is 0.10, and that's to the Z. So that's the rate 3. So then we compare that with rate number 1. The rate from the data table, 5.2 times 10 to the minus third molar per second. Then K is the rate constant. My concentration of permanganate here is 0.1 molar, and that's second order. The concentration of the chlorate is 0.1 molar, and that's again to the Y power, and then hydrogen to the Z power. So we can cancel a few things out before we go any further, just to clean things up and make it a little easier. So looking at these rates, their units, molar per second, will both cancel out. The rate constant is on top and bottom of this. They will cancel out. Let's see, we can solve that, but the units will cancel. Let's see, 0.1 to the Z will cancel out, and also the molar will cancel out. And so I'll rewrite what we're left with. 6.4 times 10 to the minus 2 over 5.2 times 10 to the minus 3 equals, and we have 0.2 to the second power, or 0.1 to the second power, and we have 0.3 to the y over 0.1 to the y. Okay, so let's go to the calculator and type some things in. All of this, 6.4 times 10 to the negative second over 5.2 times 10 to the minus third is 12.3. Point 2 squared over 0.1 squared is 2 squared. So 0.2 over 0.1, that's basically 2, and then keep the exponent. And so we're looking at this. So 0.3 to the y divided by 0.1 to the y is 3 to the y power. So we want to get 3 to the y by itself. So we'll divide both sides by 2 to the second power, or 4. And so we find that 3 to the y power equals 3.08. And then, so we want to figure out what is y, and this is really close. We're going to say that y is pretty much 1. And so we say that for y, so ClO3 minus is first order. That's what we just found, where y equals 1. So we can go back to the top and we can update this. So in our rate law, we can get rid of the y, and now we have 1. And the only thing we have left to find is going to be z. Let's duplicate this page. And again, we're going to follow the same basic process. So for this one, you want to figure out where is hydrogen changing. And hydrogen changes at trial number 4. And in trial number 4, everything else has a concentration 0.1 molar. So it would be best for us to compare trial number 4 with trial number 1. So the rate for trial number 4 is 7.4 times 10 to the minus 3 molar per second. Okay, the rate constant, we have 0.10 molar to the second power. That's my permanganate. We have 0.10 molar to the first power, that's my chlorate. And then we're looking at hydrogen, 0.10 molar to the Z power. Then my rate 1 data. So I've got 5.2 times 10 to the minus third molar per second. We have K, the rate constant. We have 0.10 molar to the second power. For the permanganate, we have chlorate as 0.10 molar to the first power. And you know what, we need to fix this. The concentration for rate 4 for hydrogen was 0.20 molar. And in rate 1, it was 0.10 molar. And that's to the Z power. So again, we can go through, we can cancel a lot of things. Units, rate constant, units. Really, you can cancel that whole thing. That. And some units. And so let's put this in the calculator. So we've got this. Should be 1.42. And over here, everything canceled out except 0.2 to the Z divided by 0.1 to the Z. So that is 2 to the Z power. So in order to solve for this exponent, that is the variable that's in the exponent, we need to take the log. So the log of 1.42 equals Z times the log of 2. Z equals log of 1.42 divided by the log of 2. And we come up with one half. And so that tells us that H plus is the 1/2 order. So Z is 1/2. And so I come back up here. Hydrogen is to the 1/2. All right, I'm gonna make some room here. So like I said earlier, usually part A for an AP chemistry test on the rate law question is going to say, write the rate law. And this is what it is talking about. It says specifically rate equals K, the rate constant, concentration of whatever to its order, concentration of the next one with its order, concentration of the next one, and so on. Usually there's only one or two. In this example, there was 3. But when it asks for write the rate law, this is exactly the format it should follow. So the next question says, calculate the value of the rate constant K, including units. And so what we do is, we have a value for rate, we have a value for permanganate, for chlorate, and for hydrogen. We have numbers for everything except for K, and so all we have to do is put all these together and solve for K. So let's use trial number 1. So the rate for trial number 1 is 5.2 times 10 to the negative third, and that's molar per second, equals, here's K, concentration is 0.1 molar for permanganate, squared. It is 0.1 molar for chlorate to the first power, and 0.1 molar for hydrogen to the first power. And so we solve for K, we're going to divide all of this over to the other side. All right, so when we solve for K, we have K equals, and I'm going to flip this around. So on top we have 5.2 times 10 to the minus third molar per second. On bottom we have 0.10 molar to the second power, 0.10 molar to the first power and 0.10 molar to the 1/2 power. And so once we put all this in our calculator, we find the rate constant is 16.4. And then units are really sort of the difficult part. So we have molar squared times molar to the 1/2, and that's on the bottom. If you look, this is to the first power, and this is to the first power, so those two we can cancel out. So we're going to have, first off, seconds to the -1, and then we're going to have molar to the -2 times molar to the -1/2. And in order to simplify that, this one's going to end up being a fraction. So what we would do is molar to the negative 4/2 times molar to the -1/2. And so you get molar to the -5/2. This example is somewhat unusual. In most cases, your orders will be whole numbers. This one's a little bit different. So in the next one, it says, calculate the rate of disappearance of MnO4 minus if, and then it gives us some concentrations. So let me erase some of this. So it says the rate of disappearance of permanganate, which is what we've been talking about this whole time. If you look at your table, this rate that it gives us is the rate of disappearance of permanganate. So we're not going to be doing anything special. We're just plugging in all the numbers that we know. So we know the value for K. We solved for it previously. 16.4 molar to the -5/2, second to the -1st. Then our new concentration of permanganate is 0.20 molar, and that one's the second power. Chlorate, 0.20 molar, that's the first power. And hydrogen, 0.20 molar to the 1/2 power. And so we're going to put this in our calculator. And we should come up with rate equals 5.9 times 10 to the -2. And then some units. So we've got, let's see how we can cancel these. So here's molar to the 1/2. And molar to the second power is molar to the 5/2. So that cancels with molar to the -5/2. And so we've got molar per second. And this is really what we should expect anyway. All of the rate values we're given are in molar per seconds. And so it's good to be able to do the units like this, but when it comes down to it, the rate should be molar per second. I think the one couple of examples of where it doesn't work like this is number 1 in your problems. So 2.1 problems, number 1. You'll want to pay attention to the units because it's actually molar per minute. And so you can just stick with those units. Don't change to seconds. It'll complicate things. Just use molar per minute. One last example. For trial number 2, find the rate of disappearance of ClO4 minus. So the rate of disappearance. This one will also help you on that number 1, the section 2.1 problems. And I'm going to write it the way most textbooks write it, and then I'm going to write it a different way, which I think is simpler. So we are looking for the rate of appearance of ClO4 minus. And so the rate would look like this, but we actually have some numbers that we can use. And we're talking about trial 2. So let's add that in here for trial 2. So the textbook version is to look at how does this compare with the rate of disappearance of permanganate, which we were given. So this is the rate of the disappearance of permanganate. This is the rate of appearance of chlorate. And it comes from the mole ratio. If you look up to the top, so the number for ClO, sometimes it's ClO3, sometimes ClO4. Oh, here we go. So the mole ratio, there are 5 ClO4 minuses for every 2 permanganates. And so we multiply the rate of disappearance of permanganate by 5 halves. And so we have 5 halves times the rate for trial 2 is 3.3 times 10 to the negative second molar per second. And you end up with 8.3 times 10 to the negative second molar per second. Now this is the rate of appearance. We are producing chlorate, and so it's going to be a positive number because it's a product. The product's going to be positive, the reactants are going to be negative. This method never really made a lot of sense to me. It does, it just takes me longer. So let me show you a possible alternative here. So what I end up doing a lot of times is something like this. So I take the original number, so we've got this right here, 3.3 times 10 to the minus 2, try that again, molar per second. And this is in terms of MnO4 minus. And the way I'm going to do it kind of frames it in more of a stoichiometry type way. I mean, they both are stoichiometry, but this is more of how I would teach you in Chem 1. And so then we look at the mole ratio. So for permanganate, looking at our paper, 2 moles of permanganate for every 5 moles of chlorate. I guess if we wanted to, we could moles, it would be the same thing as writing molar. So I'll write molar. Molar permanganate cancels, and we have molar of chlorate. And we get the same number. We're still multiplying our rate by 5 halves. We've just set it up a little bit differently. So it's still 8.3 times 10 to the negative second molar per second. And again, it's a product, so we should have a positive. These are just 2 different methods to address the same idea, changing the rate of disappearance of permanganate to the rate of appearance of chlorate.